Okay, so yeah, good morning from my side as well. So, so I've been asked to give some lectures on thermal field theory. I should start maybe with kind of a bit of a disclaimer in the sense that thermal field theory is really like a big topic. It's not easy to condense things into 4 lectures, and I think that's also maybe not the goal. So in some sense, first one might think that one learns quantum field theory and then one adds a bit and one gets thermal field theory, but really thermal field theory is in some sense it's a kind of richer framework. One can define many more observables. One needs to introduce more techniques maybe, and so it's good to keep in mind that well, if we know thermal field theory well, we can almost always take the 0 temperature limit and go to something in quantum field theory, but going in the opposite direction, it's not always obvious. And so just to mention that I do also have some lecture notes which have then much more material. And in these lectures, and somehow basically these lecture notes, if one goes through them, then experience shows that it's sort of a 2-semester course. So indeed quite a lot, and these are not, let's say, these are not advanced lecture notes. These is like an introduction to thermal field theory. So therefore. This then says that the goal for my lectures now is not, I'm not going to give a comprehensive introduction to everything that you may have already heard about thermal field theory, but it's some kind of snapshots, and mostly I would say is sort of teasers about various aspects that are important when we tackle then practical problems in cosmology and astrophysics. Okay, so that's kind of the background, and so now this is then the plan, and so today I'll try to start really from from beginning, from quite simple things, and so I will talk about fields. So why fields and particles? Well, I mean, of course, we know from quantum mechanics and that these are not really separate concepts, but in cosmology there are some issues that we like to, it's more practical to talk about them in terms of fields, and then some other problems which are more practically handled in terms of a particle picture. And this also then dictates a little bit the type of tools that one is using. But of course, at the end of the day, one should see that they are equivalent. And if one understands these different notions and different approaches and how they are equivalent, then I think one is already quite well on the way. So that's why we'll start with these 2 different approaches. And so motivation is that indeed some problems are usually thought of in terms of fields. For instance, inflation, we talk about an inflaton field. In cosmology, when we talk about the Higgs phenomenon or electroweak phase transition, then also usually we think about the Higgs field. Really as a field, in particular its expectation value, one thinks about that as a classical field. Then one could say that gravitational waves, as long as we don't have a quantized theory of gravity, then also gravitational waves, in some sense, they are classical waves. A nice example is, because this is an example where some people like to talk more about fields, some others about particles, is maybe axions. I will not say too much about that, but just to show that there are different perspectives. And so suppose now that you have some degree of freedom playing a role in cosmology that we think of as a field. And so then what we would like to learn today is basically two things. So for any of these things, one question we can ask is what we call the thermodynamics of this type of a degree of freedom. And so thermodynamics means then somehow some macroscopic properties that these fields carry. So energy density, pressure, I will mostly talk about free energy density from which one can obtain other quantities. And that's sort of very basic statistical physics. That computation of a free energy density, that's what one would have learned in the first course on statistical physics, of course, then in some other context, but the formalism is very much the same. But then there's another thing which is equally important and really quite essential for cosmology, and that is then something that one unfortunately very often does not learn in basic statistical physics, even though it is as important as thermodynamics, and that's what I would call real-time dynamics. And perhaps the simplest quantity that one can discuss in real-time dynamics is what we call the equilibration rate. Of some degree of freedom, for instance, of any of these fields. And that's really essential because that tells you whether you can use the concept of thermodynamics in the first place. If you find that the equilibration rate is so small that within the lifetime of the universe this field does not equilibrate, then you shouldn't assume that it's thermal. It just makes no sense. So it's really equally important as the thermodynamics. So this we try to kind of illustrate today. And so we start now with as simple as possible. And as simple as possible means that we start with a harmonic oscillator. And I use this to introduce some concepts, and then we will generalize these to fields. So, okay, so what we would like to compute is Z, is what we call a partition function. Well, that's the first thing we want to compute. And so in quantum statistical physics, this is the trace of e to minus beta times the Hamilton operator. So by beta, I denote 1 over temperature. The Boltzmann constant I always set to 1. And h hat is the Hamilton operator. And now in the beginning, I will even put like hat to be kind of pedantic, thus stressing that we are doing everything in quantum mechanics. And so the harmonic oscillator then means that our h hat is p squared over 2m plus m omega squared x hat squared over 2. Okay, so now we all learn in first course in quantum mechanics that we can rewrite the Hamilton operator of the harmonic oscillator in another way by introducing creation and annihilation operators, and then this becomes h bar omega a dagger a plus 1/2. Okay, so this turns out to be, of course, a very useful representation for many contexts, also for us. H bar omega is like an energy, and I'll denote this energy by sort of epsilon or a small e. And so then let's compute this partition function now. And so a trace means you take some basis of states and evaluate this operator in that basis. And now I will take the basis then of this a dagger a of the number operator. And so then the trace is the sum over all states and some goes from the vacuum state, no occupation, to infinity. And so now this is the simple thing that we can do. We can evaluate these matrix elements because the Hamiltonian in that basis and with these operators is diagonal. So we just get e to minus beta energy, and then the number operator gives the n plus 1/2. So e to minus, I take the minus beta e over half upstairs, and then the rest is a geometric sum, so we can carry it out. It's 1 minus e to minus beta times the energy. Okay, now that's some simple expression, but it kind of as such it doesn't tell much. But then the first thing we do is we define a free energy by now writing this set kind of in the same form as we started from, but now no longer the trace, but the result. The result is now a number, a function, and we write it in the same form, minus beta, but then the result we write here as the free energy. So in other words, the free energy is log of z and minus d times the log of z. So now we can then insert this expression that we have there and take the log. Log gives minus beta e over 2 minus log of 1 minus beta e. So e over 2 plus d times log 1 minus beta e. Well, it's another expression, but it still doesn't say all that much. But now we look at the third quantity, which then is really the most interesting for us when we want to generalize to field theory. And that's that we look at something that we would call like a propagator. So in field theory, propagator is the most basic quantity. With harmonic oscillator, one doesn't often use this concept, but propagator is really for me, what is a propagator? So in field theory, a propagator is something like you take two times the field operator and you evaluate it in some state, maybe with some time ordering. And so now with harmonic oscillator, the field operator really corresponds to our x. We don't, in harmonic oscillator, it's just the one, basically one can think of it as being at one point, and then there's 1 degree of freedom, and now it's our x, but here it would be the phi. So the propagator in the harmonic oscillator case, the analog is like x squared. And furthermore, if we are then doing really thermodynamics, then the x squared, more precisely, it means that we take the same type of trace as before, but now we then put there this weight, x squared, as a weight. And we are looking at this kind of an expectation value. So normalized to the partition function. Okay, so let's compute this. And if you start computing it in a silly way, it may not be such a trivial computation, but the clever way to do it is that we can think of it as a parametric derivative, because we can say that let's take the logarithm of the trace minus beta h. And now if I take a derivative of that with respect to omega squared, then I see that this acts on the Hamiltonian, and the Hamiltonian has omega squared, and so it brings down the x squared. well, it brings down also m over 2, so I have to multiply by 2 over m. And also if I take that derivative, it also brings down minus beta, so I have to still multiply by minus t to cancel that. Okay, so now I notice that minus t times the log of the partition function, that's exactly what we call the free energy. So it's really this minus t and this one I can take together, it's the free energy. And then I put here h bar squared, divide by h bar squared. Then this is my epsilon. And derivative with respect to epsilon squared I can write as 1 over epsilon derivative with respect to epsilon. There's a factor of 2, but that cancels against 2, so it's h bar squared divided by m. That. And now this we can do. We have to take a derivative of the f here. Well, the first term is pretty simple, it's 1/2. And then there's the second term, and it looks ugly at first, but if we take a derivative, then first we get something downstairs. And then we have the inner derivative, so minus e to minus beta e times then derivative with e epsilon gives still minus beta. Okay. So now we see that there's t times minus, minus is plus, t times beta is 1. And so what we really get is that the x squared is, okay, there is some factor here at front, and this we shouldn't worry about at all. This is something, well, h bar we anyway set usually to 1 in particle physics. The fact that there is an m here, that was related really to the specific definition of the harmonic oscillator. So these are kind of trivial constants, so to say, but what's important is then 1 over the energy, 1/2 plus, and now I rewrite this complicated structure by multiplying upstairs and downstairs by e to beta e. And so upstairs is then 1, and downstairs is e to beta epsilon minus 1. Okay, so that's now an important expression here. And so what we see here is well, kind of one of the most important functions in statistical physics. This is the Bose distribution. And I denote it by n Bose, a function of energy. And this is really important, and it's remarkable. Usually we learn about the Bose condensation, not quite at the beginning of statistical physics, maybe later on, but somehow it's quantum mechanics. That much is clear. What is not so clear is it relativistic? Is it non-relativistic? What is it? Here we see it really comes from the harmonic oscillator. So there's no relativistic physics here, and there's no magic. It really comes from these very, very simple manipulations that we did. That gives the Bose distribution. Then there is this factor here, and this factor here has is 1/2. Well, it has no temperature in it. There's no temperature anywhere in this part. And so this 1/2 is then what we would call the vacuum part of this propagator. So that's what one gets if one evaluates this excitation value in the vacuum state. And this is what comes from the excited states. Okay, so this is an expression that we will be needing quite a lot. So now we want to then generalize this to field theory. And so first we consider a scalar field, free scalar field phi. And well, a free scalar field is really, one can view it as a collection of harmonic oscillators, or precisely in momentum space. This is just a collection of oscillators. So now I will kind of generalize my notation a bit, so I'll now denote by epsilon k, then exactly like an epsilon there, but now in the context of a field theory, then this will depend then on, in the field theory, it will depend on the momentum. So my small k is the absolute value of a spatial momentum. And so this energy is just the usual energy that we associate with the massive particle, so k squared plus m squared. And so with this notation, then the propagator will have a similar expression, but let's start first with the partition function. The partition function will be exactly what we had, but now it's then a product of different momenta. And each time it is then like the free energy that we had, but now with each time with a different energy depending on the momentum. So there really we don't have to do any work, we can get it directly from the harmonic oscillator. Then we also want, maybe we want to have the free energy. So actually for a scalar field, now the difference to the harmonic oscillator is that now we really have an extensive system. We live in some volume, and we kind of have oscillators all over the place. And so what we want to define there is the free energy, not the free energy as such, but the free energy density. It's a more useful concept. Free energy density, I denote it by small f of phi. So that's the full free energy of the f of the phi divided by the volume. And now it's very typical to statistical physics, thermal field theory, that often we like to work for a moment, at least in a finite volume. Of course, at the end of the day, we want to take the volume to be infinity because the universe is large. But for many formal manipulations, it's quite nice to keep a finite volume for a moment, and so that we'll keep it for a moment. We take the infinite volume limit then in a second. So what would this be? So this is now, okay, so this is now minus t ln z phi over the volume. And now we plug in this expression here, and there is a logarithm here. So logarithm of a product is a sum. And then there's a logarithm of the exponential, and that gives just the argument. And the argument has minus beta, but there is minus t here, so they cancel. So it turns into 1 over volume. Out of the product with the log comes a sum, and then the log gives the the argument of the exponential. That's the free energy density. And then we still look at the propagator. And the propagator now with the field that is now more familiar with fields, so now we take a propagator. Now our fields, unlike the x of the harmonic oscillator, they live now in time and space. And so I'll take them at equal time. That's really what thermodynamics then concerns, is something at equal time. Well, equal time is very prevalent in cosmology also when we talk about some power spectrum or correlation function of temperature fluctuations. These are equal time correlation functions. So equal time is fine. I take this at equal time. Now here it's then more useful to go into coordinate space. So I take it at x and y. And then, however, the expression is again, it's exactly like with the harmonic oscillator, except that we have this sum. And now when I go then to coordinate space, then this sum, it's still a sum, but it now, from the coordinates, we also get a Fourier transform k dot x minus y. And then the rest is really, we get it from the harmonic oscillator. But now this time we put the h bar to 1, so we leave out this guy, and then the mass appears in a different way in a field theory, not like in the harmonic oscillator, but really inside our epsilon. So those prefactors we can leave out, but the rest we keep. 1 over epsilon k, 1/2 plus Bose of epsilon k. Okay, so now we already have some kind of useful expressions for a free scalar field, and in fact these expressions they don't look too complicated, but they kind of contain really lots of physics and lots of structure, so to say. We'll look at a couple of aspects of that structure. So let's say we make some remarks. Okay, so now the first thing we would like to do is, now we would like to go to the infinite volume limit. How do we do that? This is something that one should have learned it in basic quantum mechanics, but let's do it again. So the way to do the infinite volume limit, the simplest way to do it is that we imagine that we take the volume to be periodic box, as we say. So let's say that we have a periodic direction x, and the diameter here I denote by L in the x direction. And if this is periodic, then if I take some field at some point here, then it doesn't matter if I measure the distance from here or if I go around once. And so that means that in Fourier space, if I have momenta and I go around the x direction, then if I go around, then it doesn't play a role. So I should get just a kx times x. And so this means that the kx has then to be 2 pi over Lx times an integer. Okay. And so now why is this what do we do with that? Well, with that what we do is now we look at the sum. So we have this sum over all momenta. And now we see that if we implement the finite volume with periodic boundary conditions, then we can view the sum over momentum also as a sum over these integers. So I'll write it like 1 over volume times the sum over the integers. And then the volume, in my case, if I've done it with this kind of on this torus, then the volume is Lx, Ly times Lz. Okay, so what I do then is I write this as I divide by 2 pi cubed, then I have the sum, and then I have upstairs 2 pi cubed, and then downstairs I have Lx from the x direction, I have Ly, and I have Lz. That's my volume. So therefore 1 over volume times 2 pi cubed. Now that I have divided it, I have it upstairs. What I have then here is really this quantity to the cubed, so to say. And that I call, it's a volume element in the momentum space. So it's like delta, some volume element in momentum space, delta k. Maybe I write it delta k cubed to say that it's really like a volume. And so now, if one takes then the limit that the volume goes to infinity, so Lx, Ly, all go to infinity, then what we see is that the volume element here, it's this times the same for y and same for z. When the L's go to infinity, volume element goes to 0, and then I have a sum. And so in that limit, this becomes like an infinitesimally small volume element, and so out of that sum then becomes an integral. And I will denote this integral in the following by just an integration over k, but it's always defined in this way. Okay, so that's just trivial, but good to remember that from this sum we get this integral. Okay, so now now then we look at, so to say, some physics. So now we know how to take the infinite volume limit. Let's now look at this expression. And first we can ask about the vacuum contribution. So that would be then F phi at 0 temperature is what? If we set the temperature to 0, then beta goes to infinity, then e to minus beta goes to 0 very fast. Log 1 is 0, so this term drops out. Well, the log drops out, and it's also multiplied by t, so it really drops out. And so then I'm left over with only this term. And so I would then have a term like integral over k energy divided by 2. Okay, and now of course this doesn't look good. It's clearly very, very divergent. This energy grows like the absolute value of k at large magnitudes of the momenta, and the momentum itself is d3k. So this is really divergent. It's quartically divergent. So let's put a question mark. So what do we do? Well, of course, to discuss this, we would first have to, to get a value for this, we would have to regularize the theory. We have to renormalize the theory. To renormalize, we have to discuss what we mean by the value of free energy density at 0 temperature. Well, it may be related to something like the cosmological constant, and then we can start renormalizing it. And so it's an interesting and long discussion in itself, but we will not go into that because it's vacuum physics. But but it doesn't mean that it's not there. I mean, the term is there. If you do like a real computation, you should also think about what to do with this term. Okay, so we look instead at the contributions from this thermal part. And now I want to discuss two different limits, and first the low temperature limit. Of thermal part. So the low temperature limit means that the temperature is much less than the mass. The mass is, in this simple theory, the mass is the only parameter, and when we say temperature is small, we should compare with something else, and so then we compare the temperature to this mass. Okay, so what's the low temperature limit of this guy? So what we notice that epsilon k, that's always larger than or equal to the mass. So therefore, e to minus beta epsilon k is less than or equal to e to minus m over t. If the momentum is large, then the epsilon is even larger, then it is even smaller, but at least this is the upper bound. And if I'm assuming that the temperature is very small, then this is clearly a very, very small number. It's really exponentially small. And if this is exponentially small, then I can very well approximate this term by this is now really very, very small, so I can approximate it by the leading term in the Taylor expansion, in this exponential. The leading term in the Taylor expansion minus e to minus beta ek. And so therefore, we now get that the free energy density at the limit that the temperature is much less than the m is, to a good approximation, the integral of t and then minus. So minus t times integral of e to minus beta ek. And so this integral is a perfectly fine integral. It's very fast convergent. In fact, this integral is what one normally does in statistical physics. It gives this, well, it gives the number density of particles, basically. So this integral has minus t, and then there's this famous form mt 2 pi 3/2 e to minus, and in this limit, really, this is strictly speaking not an equality, it's still an approximation, but it's a leading approximation in this limit is minus m over t. Okay, so what we see is that, okay, there is a thermal correction. In this limit, it's really exponentially small, very, very small. So one goes very fast to the vacuum limit. The correction is negative. Maybe at first one is confused because we are talking about free energy density. Usually one thinks energy density is positive somehow. Well, free energy density is not positive necessarily. It can be negative. Actually, it very often is negative. And the reason is that in thermodynamics, the free energy density is not only energy density, it also has a contribution from entropy. So one may remember statistical physics, E is Ts minus P times volume plus U times N or something like that. In cosmology, we usually like to think that the chemical potentials are very small, so let's drop that. Then free energy is energy minus temperature times the entropy. So it's a Legrand transform of the energy. And so now I see if I put this on the left-hand side, I get minus B times phi. And then if I divide by the volume, I get that the small f is minus the pressure. And so pressure is something which is measurable. It's a force per area. That's positive. But then we see that the free energy is the minus the pressure. And so the free energy density, free energy can be negative. There's nothing bad about that. Okay, so that's the free energy density in the limit of low temperature. So now what we would like to do is something in the limit of the high temperature. And that's then where kind of thermal field theory becomes more interesting, maybe, becomes quite different from what happens in vacuum often. And so now what I want to do is I want to compute the high T limit Okay, we could look at the high T limit of the free energy density, but then instead I will look at the high T limit of the propagator, high T limit of the propagator. And actually we'll even simplify this. So we had this propagator, it was equal time and now we will simplify life even by sending the coordinates to be the same. Okay, so if one is used to field theory, then this is looks a bit dangerous, because usually if one takes operators at the same point, things become divergent. Again, that is indeed the case. That is indeed the case because of the vacuum part. But now we are looking at only of the thermal part, high T limit of. There is a vacuum part here that has again a divergence, but now we look at the thermal part. Okay, so first let me, why is this, what does it mean, like doing something like that? So when do we put the points, two fields to the same point? We could do that, for instance, if we are looking at if we let this field interact with something else. So let's say we have a Lagrangian, and in the Lagrangian there's an interaction. For instance, this field could interact with some coupling, kappa, maybe, I don't know what, kappa over 4, and then our field and some other field, chi squared. Then in the Lagrangian, we have really fields at the same point. And now this kind of a function would play a role, for instance, if we consider what happens to the phi if we consider sort of a loop of the chi field here. Because in this loop here we have the vertex, and in the vertex these fields are really at the same point. They're at the same point and at the same time. So what we are doing now is kind of computing this loop. But that's really quite important for us. Okay, so what should we do? Okay, so we had this integral, and now we put these two guys the same, so then there is no exponential, and then there was the 1 over ek. There was the vacuum part, which we now omit, and then there was the thermal part, which was the Bose distribution. And now we are doing this in the limit, that high T limit. So high T limit means that the temperature is much larger than the mass. And so I will then assume that my Ek, which was the square root of k squared plus m squared. So if temperature is very large compared with the mass, I will assume, kind of guided, let's say, by physical intuition, perhaps, that the typical momenta are also then much larger than the mass, and so I can approximate this energy by just the k. And then let's do this. So therefore, part of that, namely the thermal part, is integral. Everything is rotationally invariant, so I can go into spherical coordinates. dk k squared times 4 pi divided by 1 over 2 pi cubed is 2 pi cubed. Then 1 over ek gives 1 over k. And then I have the Bose distribution. Now it turns out to be helpful to actually to rewrite the Bose distribution like we had it in the very beginning when we derive it from the harmonic oscillator. Namely, I multiply this by minus e beta and now k, and then downstairs I have 1 minus beta k. Why is this helpful? This is helpful because now this number is less than 1, so we can expand again in that number. And so then we have 2 pi squared, 0 to infinity dk, 1k cancels, and then we have an expansion. Normally this would be 0 to infinity, but then there's already 1 upstairs, so it's 1 to infinity e to minus k times n over t. Okay, and now what can we do? We can exchange the limits. We can put this this here, and then I can introduce another variable, let's say x k n over t. Then dk k is dx x, but I have to compensate t squared over n squared. So then I get t squared over 2 pi squared. Then I have a sum 1 to infinity n squared 1 over n squared. And then I have the integral 0 to infinity dx x e to minus x. So now we see that with this simple trick, the sum and the integral, they factorize. And so that's now somehow very, very characteristic thermal field theory, that we get not only integrals, but we get also sums. In particular, this is very often the types of sums we get. What sum is, which sum is this? It is the Riemann zeta, particularly simple Riemann zeta argument 2, which has a specific value, which is pi squared over 6. And this is integral. This integral is a gamma 2, because in the gamma, if there's gamma s, then there's always x to s minus 1. So if there's x to 1, it's gamma 2. Gamma 2 is the same as 1 factorial is 1. So let me try to put everything together here. T squared divided by 2 pi squared. Pi squared cancels against pi squared. 1 over 2, 1 over 6 times 1. T squared over 12. Okay, so that's now sort of a very very famous expression in thermal field theory. That is really like the thermal mass correction from some other particle. If there's some other particle with which our field interacts, then this other particle, if it's thermalized, it gives us always a thermal mass correction of t squared over 12 times then the couplings from the vertex. Okay, so if one knows this, one already can get quite far in, let's say, in reading literature about the electroweak phase transition. Often the computations are not that much more complicated than this. One computes thermal mass corrections from everything. And that already, for instance, that already tells us why the electroweak symmetry gets restored, because in the Lagrangian there is minus m squared term, but then the Higgs interacts with all kinds of particles, And each of the other particles gives this kind of a correction. You multiply it by the couplings, and you add how many degrees of freedom there are, and then you get a thermal mass squared of the Higgs. And all of these corrections are positive. They always come with a positive sign, the thermal corrections, and that's why the electroweak symmetry gets restored. Okay. Okay, so now we already got some way with the thermodynamics, and now maybe I give one kind of exercise here. It's just like, really like, if you wish, it's just like arithmetics, but in fact there's lots of physics in this simple claim or simple result. The claim is the following: that prove that this propagator that we had that this can be represented in a different way, which is T sum over n minus infinity to plus infinity 1 over omega n squared plus epsilon k squared, where the omega n are 2 pi n times the temperature. N is an integer. These are called the Matsubara frequencies. And we'll also meet them later. So now it comes like out of just like as a mathematical fact that indeed this complicated, well, not too complicated, but complicated in the sense that it has complicated lots of physics in it. So this important expression can be represented in a different way. At first sight, one may wonder why would I bother to rewrite an explicit expression like this, closed expression in terms of nice functions, in terms of a sum. But actually, it turns out that in many circumstances, this expression is quite helpful. In particular, when we will look at then effective field theories and the reason that one sometimes needs to do a reorganization of the perturbative series, even if the coupling would be very small in some theory, one still may need to do like a resummation, that as we call it, so reorganizing a perturbative series. These kind of theoretical issues are often much simpler to understand with this integral representation. So that's why it turns out to be a very useful representation later on. So, I mean, it looks like a simple exercise, but it's not quite that simple, and so it's quite nice if one manages to do it. Okay, maybe are there questions at this point? Yes?
I'm a little bit confused about how I'm supposed to think over this t squared over 12 correction, because we got to this from a completely free field theory, and then somehow this term seems to capture information about interacting theories.
Yes. Well, but because the interaction is here, like in this vertex, but then maybe this field is still weakly interacting. So I mean, that's the usual perturbative. Then we are accounting for interactions in terms of a perturbative series. So the couplings are in the vertices, but then the propagators may still be like free propagators. I mean, that's the usual way of doing perturbative Feynman diagrams. Yeah, sorry, I didn't repeat the question. The question was, how is it that by doing free field here, we can account for interactions? And so the answer is the interactions are in the vertices if the couplings are small. Anything else? Okay, so then let's go on. And so now we want to go to this other part of what we would like to do, and that is somehow this real time real time. So now, so the question is really how the fundamental question is when is temperature a useful concept? I mean, we just kind of postulated that we compute the partition function or a free energy density or so, but it's not guaranteed that the physical system kind of wants to obey our postulate. We have to somehow give arguments for why this is the case. And so again, I want to do it with a simple example, and this example is basically, it is really as simple as it can be, but with real time and temperature. It's kind of it is a generalization of the harmonic oscillator, and in particular of the free scalar field. So that's what we want to do. But before that, I want to sketch a picture which is very useful for keeping in mind. Let's call it big picture. And this big picture is basically, now it's just a sketch, but somehow what's behind it is what then, if one wants to search for the theory behind it, it's called the Landau theory of thermodynamic fluctuations. And so the big picture looks like this, that we now look at things as a function of time, of physical time. And then we look at something, and I'll put here phi as if it were the field. So more precisely, I should take like the phi maybe like averaged over some small volume or so. And then I put here phi bar, and the phi bar would be the equilibrium value of this field. So this is what we would get if we would compute this value from our postulate that there is a temperature. So now, then, however, in general, there's no reason to state that we obey this postulate at the beginning. So we can say that we start from somewhere, like here. And the question is what happens? And so now so now the first thing is somehow I think sort of the intuition is that usually if we let time run, then let's say entropy increases. We forget about the past. We eventually systems don't have memory about what happened long ago. One loses information, entropy is maximized, one approaches equilibrium. So that's one part of the answer, that we think that the system, if there are interactions with something, it should go towards the equilibrium state. But now that somehow the deeper point is that if you go in this direction, okay, you lose information, so to say, about the initial conditions. Maybe the initial condition also had some extra energy. One loses energy, but in the end, energy is conserved. So you cannot just lose something. You cannot lose information. You cannot lose energy. They have to go somewhere. Well, they can go to the degrees of freedom of this plasma or whatever with which this field interacts. But if energy and information can go in that direction, they should also come back sometimes. And so that's what really Landau theory then says, is that, okay, it can be that you go there, but you never go exactly there somehow. Then there are also fluctuations here. And these fluctuations is where then the thermal medium, the plasma, gives back energy and information, if you wish, to the field. And so what we say here is that there is a period, if you start far away from the equilibrium, there's a period of what we call dissipation. That things are dissipated, dumped away, what we had in the beginning. But if that's the case, then necessarily there is also another period of fluctuations where we gain something from the medium. And then ultimately these two things are not separate. They are not independent phenomena. They are deeply connected. That's what the theory says. Okay, so now we want to understand that a bit. And so therefore we take like a prototype. Like we want to do some equations. We want to see how this could be the case, how it could be implemented. And so the prototype it is like the scalar field theory, but now made richer in that it includes this dynamics. And that prototype theory, it's Langevin equation. Langevin equation also can mean different things, but it's one version of the Langevin equation. So what do I mean by that? So we take our scalar field, and so let's first write now an equation of motion as if there were just a scalar field in vacuum. Then the equation of motion is the Klein-Gordon equation, d mu phi plus v prime phi is 0. But I leave this empty because we will add something there. Okay, so this is like the Klein-Gordon if there would be zeros everywhere. Okay, I will use, I will say this because in cosmology it's not always obvious because some people use a different signature, but in these lectures I will use plus minus minus signature for the metric. And this is the potential or effective potential if you wish. Okay, so now what do we do? So the point now is that if we let this field, our phi, interact with something else, some plasma, some heat bath, then there is a special frame, namely there is I have a four vector, 4 velocity, we'll call it u mu. Is 4 velocity of heat bath. And if I have such an object, if a special frame exists, then I could add here a structure which is in some sense even simpler than this structure, namely I can add a first derivative structure. And then of course I have to put here a coefficient, gamma. And this coefficient is this is what we call in this equation then the equilibration rate. Okay, so now what you kind of see is, I mean, this is the D'Alembert operator, dt squared minus dx squared, and this is the first derivative. So actually, this is sort of friction. It's like the first derivative. The time component thereof gives phi dot, and phi dot is what we associate with friction. And in fact, that is the physics that this term introduces. It introduces this dissipation, this friction. If one starts the field from somewhere, then if it's evolving, if its phi dot is non-zero, like here phi dot is non-zero, it is sliding down somewhere, then this term is on, and this gamma says how much, as a consequence, it loses energy to the heat path. So energy is not constant. This is really like a dissipative term. It's dissipation. However, we already learned that if that's the case, if we lose energy, we have to also gain energy. And so that's why we put another term on the right-hand side, xi. But where we gain energy from is this heat path. And the heat path, if that is thermalized, there is really no information. There is minimal information. So therefore, this guy, we say we take it as noise with no information. No information means that this noise has average 0, and then it has a 2-point function, which has some amplitude, and then otherwise no information. Uncorrelated, unless you're at the same point, then it cannot be 0 because you have something positive, then there is some correlation. I use the notation because in thermal field theory we often have to discuss separately time and space, and so therefore I use these small letters like the small k for the spatial momentum and also spatial vector, and then capital letters I use like for four vectors, in this case for space-time volume. That's the Langevin equation. Now it's really, if you don't like it, you can always put these terms to 0 and you go back to Klein-Gordon. So it's not, you can always restore vacuum. That's good. Then of course, if we add something, one may ask, should we add something more? Is this the full set of things that we should add? And in some sense, we'll come back to that in a moment. But now we take this as a simple example. So now, so now the question is what? First I want to discuss briefly, sort of in parentheses, something which is quite important, but I didn't say anything about it so far. Which is that everything I did so far was in Minkowskian space-time. And so, of course, in cosmology, that's not the case. We have a metric. If I keep my signature, then the Friedman, Robertson, Lemaitre, Walker metric looks like this. There's a scale factor here. And so A is the scale factor of the universe. The universe expands. So now, of course, if I have a covariant equation here, it's trivial to write it in a general covariant form. I just replace the derivatives by covariant derivatives. Everything is fine. That's more like that's sort of just mathematics, so to say. But it's also important conceptually because really one reason why this real time is so important in cosmology is that because of the expansion of the universe, we all know that we always say universe expands, temperature goes down. So that already says that the thermal state, if there is a thermal state, it is changing. And so that in itself poses a question, okay, if the thermal state wants to change, then do the microscopic interactions, can they follow this would-be change? Are they efficient enough to stay in equilibrium? Or are they efficient enough to reach equilibrium in the first case? So actually the fact that we are in an expanding universe, it has some mathematical implication. We should rewrite the equation not in Minkowskian spacetime, but in an expanding background. But it also has very important physical implication, which is that this question about the real time, about the equilibration, it necessarily always becomes extremely important in cosmology. And so that's just another reason why we have to think about the real time. So now, however, I was doing everything in Minkowskian, so let me just well, maybe it's another exercise. That then the Langevin equation takes the following form. From here we would say there is phi dot dot, but then there's another term which is 3 times h times phi dot, and then nabla squared phi, and then other terms which basically remain the same. We don't need to discuss them, but there is this important term here, and h is a dot over a is the Hubble rate. And so now what we see is that this Hubble rate here, it's quite a bit like this friction here. In particular, if we took this u to be a rest frame, so that it's only the time derivative, then there is like a physical friction here, gamma times phi dot, and here there is a friction caused by the expansion. Well, why does the expansion cause friction? It's because of the expansion, well, wavelengths redshift, and so one is, so to say, losing energy just to the expansion, and that is like friction. Here one is losing energy to the medium, here one is losing energy to the expansion, but mathematically speaking they play very similar roles. But again, that's another motivation for considering both, if you wish. Okay, so now I want to come to the what we would like to do, and let me what we would like to do is the following. So let's consider a special limit. We are in the heat path rest frame. This means that the forward velocity really becomes 1, 0. We place ourselves in this frame. We take a free scalar which means that the prime of the potential is m squared times phi. And so then so now to keep life simple, we stay Minkowskian. And so then we have an equation which says dt squared minus nabla squared plus gamma dt. This comes from this term with if we are in the rest frame of this guy. And then there's plus m squared. Phi is psi. And the only thing we need to know about the psi is that its average is 0 and its 2-point function is white noise. Okay, so what is this? This is a linear second-order differential equation with an inhomogeneous term. We all know how to solve it. We find the Green's function, then the Green's function, then we integrate over the source positions with the Green's function. And the Green's function, if it's like a linear equation, well, a linear equation like that, actually the Green's function we can write in a Fourier representation, of course. Such that if we operate on this, we get 1, we need to get 1, and so therefore we have minus omega squared plus k squared minus I gamma omega plus m squared. That's the Green's function. And now, what would we like to do? Well, what we like to do is not, then we know the solution. And so what we like to do is to compute exactly the same as we did in the first part of the lecture. So compute the 2-point function. That's then the, let's say, third exercise, which is compute phi equal time 2-point function now from this Langevin equation. So let me draw a picture to illustrate what should happen. So we have time, we have space. Then what this equation says is that sometimes there is noise somewhere, and it sources a phi by the Green's function, and that sources a phi. And then there can be noise somewhere else, and that sources another phi. This is the propagator, Green's function sources, and then the phi. And now we take a 2-point function of this guy here. We take them at equal time, but separated by space. And so this is a well-defined exercise, but it's quite interesting. And I'll give you the answer. The answer looks like this. It can be done. There are some integrals which are not quite obvious at first sight, but they can be done. Out comes omega divided by 2 gamma. That's already weird. We would think that you can take gamma to 0, but oops, there is 1 over gamma. And then k epsilon k squared. Okay, so now we can recall thermodynamics. Recall thermodynamics, which said that this answer should be well, what should it be? Well, we had 2 representations. This one, well, it doesn't look so good, but then we had another representation. Which was t times omega n 1 over omega n squared plus ek squared, where omega n was 2 pi tn. And now we see that actually we can match these. We can match this if we consider only the omega n to 0 part from here, because then we get 1 over ak squared. Why would we only consider that? Well, we'll come back to that. If we only consider the omega n to 0, then we have t over ak squared. Well, here we don't have t over ak squared, but we get that if we impose that these coefficients are related by this relation, and this relation is perhaps the most famous relation in non-equilibrium statistical physics. It's called the fluctuation dissipation relation. Also in the context of Brownian motion, where many of these things were first discussed, it's also, it's related, or it's related to what is also known as the Einstein relation. So Einstein also thought about Brownian motion. And so we see that actually this Langevin equation, it seems like it's not the full world, doesn't give everything, but it gives a specific term, and in a certain limit this specific term may be important, but it gives this specific term only if the fluctuation coefficient and the dissipation coefficient are related in a certain way by this fluctuation dissipation relation. Okay, so then the message is that that this Langevin equation, at least it gives in a certain limit, it says how the system equilibrates. It reproduces the equal time correlation function, but it has more information. It also tells what happens at non-equal times. It has more information, and that's why it has also more parameters, in particular the gamma, the equilibration rate, and the omega. And the gamma tells how fast this process takes place. Okay, so that's more or less what I want to tell today. Are there questions? Yes?
So I didn't quite get what is the name of the letter, the chi parameter on the right-hand side of the equation.
Psi, yes.
What is that noise exactly? Is it the noise of the...
Yes, the question is what is the psi, what is the noise? And so, so it's really this, the idea is that we have this field phi, and then there are some other particles, other fields. And these other particles and other fields, they interact with themselves and they form some kind of a heat path, which we call T. Well, which we say that is at a temperature T. And this phi is evolving in this background of the other fields. And now this phi, if it starts somewhere, it can lose energy by scatterings to these other particles. And that's the dissipation. It gives energy to them, that's the dissipation gamma. But then the whole system you should think of, the whole system you should think of it as closed, so to say, like the whole universe or so. So if energy can go from here to here, then energy can also go in the other direction. Energy can also go in the other direction. But this part is thermalized. So it has no information. Basically, temperature tells everything about this system. There's no other information there. So if it gives energy back, it does it in a completely random way. There's no correlation or so. It's completely white noise. And that's what this noise does. This psi gives energy back to the field, but it does it with minimal information. Okay, no more immediate questions. So then tomorrow we go to this particle picture, but in some sense we want to also with the particles, we want to kind of, the language will be completely different, but basic concepts, basic physics are in some sense quite similar. So there are particles, they can get corrections, thermal masses and so forth, but also very importantly there is a certain rate which says how fast these particles want to equilibrate, how fast they interact, and how we describe it. It can be different and formalism is different, but the basic physics really this equilibration and equilibration rate, and the process is going from phi to the heat path and vice versa. This is very important, will also play a role tomorrow. Good, so then time for a coffee break.